Hello and welcome to another video in the PowerPoint series from movieelectrons.com. Our topic for today is voltage regulation. Now, voltage regulation question can be asked for different sets of equipment, for a motor, for a generator, for a transformer. We're going to deal with the transformer today, just because I think, in my view, it has the most practical application. Um, so let's read the question before we get into solving it and discussing a little bit of the theory about voltage regulation. So what we've been asked is, what is the percent voltage regulation of a 1 kVA 110 to 220 volt transformer for which the measured no load primary voltage is this and full load secondary voltage is this, and we've been given four options. So what I've done here is I mentioned some of the formulas that we'll be using, and I'll get into those a little bit. This is the formula that defines the percent voltage regulation, and this is just a reminder that the turns ratio or the voltage ratio in this case is V primary or V secondary is a constant A, and we'll be using that in our formulation. Before we go ahead and get into the solution, let's do a quick definition of what voltage regulation is. So that'll help us to understand this a little bit better. So regulation is defined as the difference between um, the no load between the no load and full load voltage magnitudes let me spell that correctly. Voltage magnitudes. There you go. So it's the difference between the no load and the full load voltage magnitudes with respect to the full load voltage magnitude, and it is expressed as a percentage. So what that tells us is that percent voltage regulation is the difference between the no load and the full load voltage magnitudes. So no load minus full load with respect to the full load voltage magnitude, and that's this expressed as a percentage. So that's what the definition of voltage regulation is, and that's what I mentioned in the formula here. What I've added here is the S, because for a transformer we're going to use the secondary side. So we're going to see the secondary no load minus the secondary full load with respect to the secondary full load expressed as a percentage. Let's get into the transformer circuit for a bit, just to understand what's happening here and to see how voltage regulation is important and what that means in a real world scenario. So what I've drawn out here is this is the equivalent circuit as seen from the secondary side. Where do we get this from? We get this from this. So if this is the core of the transformer. This is the primary equivalent circuit, and this is the secondary equivalent circuit. What I've ignored is the shunt resistance and reactances, because it's been found that they don't have much of an impact on the voltage regulation. So if you look at this, you have your R primary and your X primary, same here on the secondary side. You have your number of turns ratio, which is equal to your voltage ratio. From here, if we see everything on the secondary side, we get an equivalent circuit here where R equivalent secondary is nothing but R primary plus R secondary, where R primary prime is nothing but R primary over the square of the turns ratio plus the R secondary, and similarly you have your um, x equivalent is equal to x primary prime plus x secondary, which is equal to x primary over a square or x secondary. So this is how we get from the primary circuit, when we see it on the secondary side, we get an equivalent circuit, something like this. This all comes from transformer theory. You can go and review that if you like, if these look a little unfamiliar to you. The other thing to notice is, if you notice the circuit, this right here, if you measure the voltage here, that's the voltage on the secondary side when no load is connected. And when you have a load connected, you have a load connected here. So this voltage is the voltage on the secondary side with full load, right? So that's what we've drawn out here, and that's the secondary current. If we evaluate this circuit, this equivalent circuit, what you're going to get is, you're going to say voltage secondary no load is equal to the voltage drop here, which is nothing but I secondary times R equivalent secondary plus J equivalent, sorry, X equivalent secondary plus the voltage on the secondary side full load, right? So the voltage drop here across this resistance and this inductance plus the full load voltage here is going to give us the no load voltage. Now this gives us that secondary no load voltage minus the secondary full load voltage is nothing but the voltage drop here. And this, if you notice, is what's on the numerator side here. If you look at the formula that I mentioned, secondary no load, of course that's just magnitudes, but in essence what we're looking for, the voltage regulation is defined by the voltage drop that's happening here. Now what is this voltage drop dependent upon? Now the I here is a vector, so I is actually I secondary magnitude and an angle. This angle is dependent on the load. It's the gives us the power factor of the load that will be connected. So what that tells us is that the voltage regulation is actually dependent on the load. As the load changes, the voltage regulation will change, and therefore your voltage regulation changes. And that's why having the value of voltage regulation is important. What happens is, when the transformer, for example, here is lightly loaded, you would have a voltage rise, and when you have it when you increase the load, your voltages will come down. Now this difference between light load and heavy load durations needs to be controlled and needs to be minimal. That's why when you buy a transformer, what you'll be given by the manufacturer in the test data is, what they'll give you is, they'll give you different voltage regulation values at different power factors. Now let's say you're buying a transformer from vendor A, you're comparing from vendor A to vendor B. If everything else is the same, but if vendor A has a voltage regulation of 2%, whereas voltage B has a regulation of 5% at, let's say, a power factor of 0.9, then you'll go with vendor A, because their voltage regulation, what that's telling you, the 2%, is that even at even when the conditions are when the load conditions change, the voltages will not change that much. They'll only change by a 2% margin. So that's a good thing, and that's where voltage regulation is practically used. So I just wanted to give you a feel of that, wanted you to understand that, and that's why I did this explanation. It has really nothing to do with our with solving the problem, which is relatively straightforward. You can just go ahead and use the formulas that I mentioned above. So let's get back into the solution. So if we, let me write that formula down here again. You're going to have no load magnitude minus the full load magnitude over the full load magnitude times 100%. So let's put the values in. The thing to remember here is, okay, if you go back to the question again, what have we been given? We've been given primary voltage at no load. Well, primary voltage at no load, this is, right, Now what we do know is V primary over V secondary is A. So what that means is V secondary is V primary over A, which implies what we can write this then as is equal to, um, so this we can use that to find out V secondary no load can be written as V primary no load over A. So we're going to use that, and we've already been given secondary voltage, the full load secondary voltage. So we have that value. So let's go back here. So what we can write this as is V primary no load, which we've been given, over the turns ratio or the voltage ratio in this case, and this remains as is. So we can just plug the values in and we can get our answer from that. So if we plug the values in, we've been given V primary as, so we're just interested in the magnitudes. Remember, we don't worry about these angles. So 112 and 220. So what we can write that here as 112 over 0.5 minus 220 over 220 times 100%. Where do we get the 0.5 as? That's because A is, we've been given the primary voltage is, the rating of the transformer is 110 by 220, right? So that's what we'll have this as, 110 by 220, which gives us 0.5. So if you plug this in your calculators, you should get an answer of percent voltage regulation should come out to be something like 1.82%. And let's go look at our options. There you go. And so option B would be the correct answer here. All right, so I hope that was clear. I know I went a little bit quick with the equivalent circuit there. Just take your time to absorb that. If any of this is not clear, I'll encourage you to go back to your transformer theory and just review those notes there. But the reason I wanted to give you an explanation of that was just so you understand practically where we use voltage regulation, how it's important. As I said, the question can be very easily solved using these formulas. So what I'll do is I'll leave you with a sample problem. It'll be a little bit simpler than even this, because I'm not even going to give you a transformer problem. I'm just going to give you a simple problem for the bus. So let's say find percent VR at a bus where your let's see, the no load voltage is equivalent to 1.02, and that's the angle, and your full load voltage is, let's say, 0.98, and that's the voltage. So go ahead and find the solution for this. Leave your answers in the comment section below. If you have any problems solving this or understanding anything that I mentioned up here, feel free to leave your comments or send me an email at nimish@movingelectrons.com. And I hope to see you in the next video. Take care. Bye now.